Welcome to the final lesson of pre-calculus. This is section 11.5, the area problem. At the end of this lesson, I will be able to understand the term summation, find the limits of some summations, use rectangles to find approximations of shaded regions, and use limits of summations to find areas of plane regions. Let us begin. First thing we need to do is we need to understand what a summation is. You will also hear this called a series. So a summation and a series mean the same thing. What is it? Well, first thing we do is we take a sequence. For example, take the sequence 1, 3, 5, 7, and so on. Summation takes all those terms in the sequence and adds them together. Now, can you think about this? Sequence, what did we say models the sequence really well? A function models the sequence really well. So look at this this sequence right here, and tell me what function models that sequence. Take a second, pause the video, and think about it. Here is the function. So when n equals 0, a sub 0 equals 1. 2 times 0 is 0 plus 1 is 1. When n equals 1, 2 times 1 is 2 plus 1 is 3, and so on and so forth. So here's our function. Now, next question. What is the summation of that sequence listed above, going on forever? Like so. It's infinite, right? Makes sense. Now, notation, again, series notation or summation notation is this. Okay, you will see this piece right here. You will also hear this called sigma, after the Greek letter sigma. Looks like a big capital E with some fanciness put in there. That is telling you that you're summing this function right here. So let's unpack the notation a little bit more. First thing I want to go into is a sub n is the function for the sequence. Now, n is the variable, and 0 in this case is my starting point for that variable. So our first term is when n equals 0, and then my last term is on top of my sigma. Now remember, n is always going to be in the natural numbers. So n will never be a number that is negative. So n will never equal -1 or -2 or anything below 0 right there. Furthermore, it'll always be a whole number. Remember, sequences have the domain of the natural numbers. So the natural numbers start at 0 and go up by ones. 1, 0, 1, 2, 3, 4, and so on. So n will never equal 1.28 or something along them lines there. Remember that. So in the case of this sequence where a sub n equals n squared, the summation from n equals 0 to infinity of a sub n simply equals, when n equals 0, it's 0 squared. When n equals 1, it's 1 squared. When n equals 2, it's 2 squared. When n equals 3, it's 3 squared, and so on and so forth. So to simplify this, we would say 0, 0 squared is 0, 1 squared is 1, 2 squared is 4, almost made a 2 there, 3 squared is 9, 4 squared is 16, and so on and so on. Now, it's pretty easy to see that this sequence goes to infinity. So this is what we call a divergent sequence. Now, you will also see this placeholder variable right here, this I. Okay? What is the point of that new variable? We use this as our variable so we can use n to represent some generic n to a finite summation. So let's see what that means. And we're going to start by looking at the properties of summations or series. So my first property of summations is the constant function. So c is a constant, and I go from I equals 1 to n of the constant function, then that equals c times n. If I have two sequences added together, and I'm summing the sum of those two sequences added together, right here I'm adding two sequences are my function. So I got two sequences right there that are being added or subtracted from one another within the summation. When I see that, I can simply split those apart into two separate summations. And the plus or minus right there matches whatever that is, plus or minus. My next one, if I have a summation times a constant, in this case k is my constant, when I have that constant in front of a summation, I can simply bring that outside and I can do that. Okay? Next, if I have, now what is this? This would be, I'll give you an example. This is 1 plus 2 plus 3 plus 4 plus ... all the way to plus n. When I have that, I can use this expression to evaluate. And the reason I got a star there is we are going to prove that. Next, let's move this up, move this over. Oh, I didn't put my n there. There. Now I'm going to show you the square function. This is, so if I am summing I squared from 1 to n, this is how I evaluate it. And then lastly, the cubic function I can evaluate this way. So the reason I got the star on number 4 is because we are going to prove that, so let's prove it right now. So let's prove property number 4. So as you can see, I've got it printed out. The sum from I to n equals I. Or I'm sorry, the sum of the I function from I to n equals 1 plus 2 plus 3 plus a bunch of stuff in the middle. And then the last three terms are, well, n is the last term. The one before that is n minus 1, or 1 less than n, and the one before that is n minus 2, or 2 less than n. And what I'm going to do is I'm going to use the distributive property, I'm sorry, not the distributive property, the commutative property, to write these in a certain order. I'm going to write those two first. So this is going to equal, and this is n plus 1, because I got the n and 1, and I'm adding those together. Okay? And then I'm going to bunch that, I'm going to add that to those two. So this is plus 2 plus n minus 1. And then I'm going to do these two together. And that is 3 plus n minus 2. And then plus dot dot dot. Now, think about this. I've paired two terms with each other in each case. In the red case, I got one pair right there. In the second case, I got another pair right there. In the third case, I got another pair right there. How many total pairs? Well, I got n terms, so I'm going to have n over 2 pairs. And that's important because here is the nice thing about this. Let's go down to this next step again. N plus 1 simply stays n plus 1. How about this? How does this term simplify? Well, n minus 1 plus 2 is going to simplify into n plus 1. And then we're going to simplify this term. Well, what's 3 plus n minus 2? That is also n plus 1. And each time I add something to it, I'm adding another n plus 1 to this whole thing. And how many times am I doing it? I'm doing it n over 2 times. Well, I got repeated addition. How do I simplify repeated addition? I can say that's equal to n over 2 times n plus 1. And if I simply write that over a single fraction, that is n times n plus 1 over 2. And we have just proved the summation property number 4 on the previous page. So let's use our properties of summations to evaluate this expression. So we want to know the sum of this function from I to n. So this equals, well, I can remember in this case 1 over n squared is a constant. So I can say this equals 1 over n squared times the summation from I equals 1 to n of I plus 2. That was property number 3. Now my next step is using property number 2, which says I can, when I have two things summed up right here, I can simply split it off into two separate summations. So I'm going to do that right now. I equals 1 to n of 2. Now, Why did I put brackets around? Why did I put the brackets there and there around it? Because both terms, both summations, get multiplied by 1 over n squared. I can't do one and not the other. Now, we are going to the next step, which is to substitute, and we're going to use property number 1 and number 4. So 1 over n squared times, and what is I? Well, that is n times n plus 1 over 2 plus, and this is simply 2n. This one is property, this is property 1 and this is property 4. Next step, distribute the 1 over n squared. So I got n times n plus 1 over 2n squared plus 2n over n squared. Now I'm going to find a common denominator, so this needs to be multiplied by 2 over 2, and I also need to distribute the n to both terms in the parentheses. So this is going to be n squared plus n over 2n squared plus 4n over 2n squared, which then equals n squared plus 5n over 2n squared. Now, you can rationalize. To evaluate this further, you can either rationalize and multiply both the numerator and the denominator by 1 over n squared, and you will get 1 plus 5 over n over 2, and then you can do direct substitution. You know this goes to 0, so this would equal 1/2, and that is your answer. But you also know that you have a second order polynomial divided by a second order polynomial, and you can just divide by the leading coefficients. So that'd be 1 over 2, which also gets me 1/2. So we have evaluated this summation. Now, we can combine our understanding of summations with our understanding of limits. And we're going to find the limit of an infinite sum. In other words, we're going to find the limit of a finite sum ending at n as n approaches infinity. So I want to find this limit, or this sum. Okay? So the first thing I'm going to do is I'm going to recognize that this term right here is a constant. So I'm going to bring that out. This equals 1 over n times the sum from I equals 1 to n of 1 plus I over n squared. Now, I have to square this function because of this guy right here. So let's do that. 1 over n times the sum I equals 1 to n up, let's see, that's 1 plus 2I over n plus I squared over n squared. Okay, now I can use property number 2 as follows. One over n times the sum from I equals 1 to n of 1. And then this guy right here, the part that I'm circling, is a constant. So I'm going to bring that out in front of this. And then plus, this is my constant in the denominator, like so. Now, what I'm going to do now is I'm going to evaluate each of these three. This is property number 1, this is property number 4, and this is property number 5. So let's do that. This equals 1 over n times n, right? 1 times n, or just n. This one is 2 over n times n times n plus 1 over 2. And then this one is 1 over n squared times n plus 1 times 2n plus 1 over 6. And then I finish my bracket. Now, I'm going to distribute everything through here. I'm going to distribute this 1 over n to all of the terms, and I get 1, because 1 over n times n is just 1, plus this cancels out with that, that cancels out with that, and then I get 1 over n times that is n plus 1 over n, and then I get this cancels out with that, and I get plus n plus 1 times 2n plus 1 over 6n squared. So now I'm going to scroll a little bit more so we can continue our work. This equals, let's see, let's get a common denominator for everything. So the common denominator is going to be my 6n squared. So this is going to be 6n squared over 6n squared plus, let's see, this is 6n squared plus 6n over 6n squared plus, and I'm going to multiply these. This is 2n squared plus 3n plus 1 over 6n squared. Add my like terms. 6n squared plus 6n squared plus 2n squared, that's 14n squared. 6n plus 3n, that's plus 9n plus 1 over 6n squared. Again, you can, let me fix that. You can either rationalize by multiplying 1 over n squared over 1 over n squared by that fraction, or you can simply use that leading coefficient rule, because I have a polynomial of degree 2, or of order 2 rather, divided by another polynomial of order 2. So I can just use the leading coefficients, and that's going to equal 14/6, which simplifies to 7/3. And there is my answer. We can use that same strategy to examine the area under the curve shown there between the values of 0 and 4. So we're going to find this area. I colored outside the lines a little bit, forgive me, but that's the area that we're going to find. I'm going to show you how. So we want to break this region down into rectangles in order to approximate the area under the curve between x equals 0 and x equals 4. So the most rough example of breaking this down into rectangles is to break this down into a single rectangle. Now I'm going to pop this up, and there's a single rectangle. As you can see, it's a very rough estimate. Now, if I break it up into two rectangles, it doesn't look much different. However, if I break this into 4 rectangles, now the area of those gray rectangles looks something close to what the area under the curve may look like. Let's do this further. Now, if I break this up into 8 rectangles, you'll see something that looks very close in area to the area of my curve. How many rectangles would I need to make the area of the rectangles equal to that area under the curve? And if you remember to the last lesson, we talked about summations. And basically what we're doing is we're adding the areas of rectangles together. How many rectangles would I need, and how wide would those rectangles have to be in order for me to have an exact figure for the area underneath this curve? If you thought we would need an infinite number of rectangles, you'd be absolutely right. And we just learned how to do summations equaling infinity. So let's break this down into some language that we've used. Remember, how high is this rectangle? Well, it is simply the value of the function at this upper right-hand corner, right there, of each rectangle. And how wide is the rectangle? The rectangle is the interval from 0 to 4 divided by the number of rectangles. So let's call the 4 B, and let's call the 0 A, and you'll see why in just a second. What is this hot mess that we got right here? Well, let's break these equations or these expressions down a little bit, shall we? First of all, we talked about infinitely many rectangles. Well, here I have n is going to infinity. So I have n being the number of rectangles. Remember, I assign B and A accordingly. B was the right-hand side of my selection, and A was the left-hand side of my selection. I is which rectangle? So this is I equals 1 is the first rectangle. I equals 2 would be the second rectangle. I equals 3 would be the third rectangle, and so on. All the way up to the infinite numbered rectangle. Clear as mud yet? It gets better. Because for this problem, a was equal to 0, it made things really easy. But what if a is not 0? How do I find the first rectangle? Well, I have to start at a, and then I have to add the width of each rectangle, and then I have to multiply it by the ith number of the rectangle. And then I have to evaluate that number at f. And that gives me the height. This green bracket here gives me the height of the ith rectangle. The nice thing is, because all these things are the same width, this is being multiplied by the width of the rectangle. Okay, so the yellow part that I circled, this part right here, is a constant. So then I can just simply bring that out, and then I have, and I'm going to write it down here, the limit as n approaches infinity of the sum of the area of all the rectangles. I equals 1 to n of, I'm going to bring, I forgot what I was going to do. I was going to bring the yellow out. So the limit as n approaches infinity of b minus a over n times the sum as I equals 1 to n of f of a plus b minus a over n times I. And there is our expression to find the area under the curve. And the reason I brought the yellow term out in front of the summation is so that we don't get confused as to what we're doing here. So let's find the area under the curve between 0 and 4. So a is 0 and b is 4. I've written what f of x is in the corner here, and you see it right here as well. You see it right there as well. Now what I'm going to do is I'm going to move this over to the side so that I have more room to work. Now the area under the curve, as we've covered before, is the limit. Is the limit as n approaches infinity of b minus a over n times the sum from I equals 1 to infinity of f of a plus b minus a over n times I, and so that's our formula. So we're looking at the limit as n approaches infinity of, let's put our variable, our substitute numbers in for our variables. Remember, b is 4, a is 0, so 4 minus 0 over n times the summation from I equals 1 to infinity of f of 0 plus 4 minus 0 over n times I. Now I've substituted variables. I'm going to simplify. 4 minus 0 is 0. So I got the limit as n approaches infinity of 4 over n times the summation I equals 1 to infinity of f of, remember 4 minus 0 is 4 over n is 4 over n plus 0 is just 4 over n times I. And this right here is a simplification of this right here. Now I can start evaluating my summation. So I'm going to move this up and we're going to keep evaluating. But before I do, I want us to remember that f of x equals negative x squared plus 6x. I'm going to put that in a box so we don't forget it, because the next step is going to have us say the limit as n approaches infinity of 4 over n times the summation from I equals 1 to infinity, or I'm sorry, not infinity, I gotta change this up above too. You guys gotta catch me when I do this. From I equals 1 to n of, and now I'm going to evaluate f of 4i over n, so that is negative 4i over n quantity squared plus 6 times 4i over n. Okay, now here's what we're going to do. We're going to split this summation up into two separate parts, because from our rules and properties of summations, if I'm adding two parts of a function like that, I can just split them up into two summations. But I have to remember that I am multiplying both parts by this 4 over n. So let's do that. The limit as n approaches infinity of 4 over n times, I'll make a bracket there, the sum from I equals 1 to n of negative, and I'm going to square this, so it's 16i squared over n squared plus the sum from I equals 1 to n of 24i over n. And then I end my bracket. And I'm going to move this up a little bit more. Now I can do some more work. Remember, everything is being multiplied by this 4 over n. So the limit as n approaches infinity of 4 over n times. And now, properties of summations, I'm going to bring the negative 16 over n squared out in front of my first summation from I equals 1 to n of I squared. And you should be starting to see what it is that I am doing. I went too far too soon. I got to bring the 24 over n out of the second one. 24 over n times the sum from I equals 1 to n of I. Now, just to make things a little bit easier, I am going to distribute the 4 over n to both parts, which is going to leave me with the limit as n approaches infinity of negative 16 times 4 is negative 64 over n times n squared is n cubed times the summation from I equals 1 to n of I squared plus, and then 4 times 24 is 96 over n squared times the summation from I equals 1 to n of I. And now I can apply my properties of summations. Which ones? Well, the red one here that I just underlined is going to be property 5, and the blue one right here is going to be property 4. So let's go over that real quick, shall we? The limit as n approaches infinity of negative 64 over n cubed times, and I'll put this in red, n times n plus 1 times 2n plus 1 over 6. That is property 5. Plus 96 over n squared times the quantity, and here's property 4 in blue, n times n plus 1 over 2. Let's put that in parentheses as well. Now I can start doing some simplification. The common denominator on this is going to be 6n squared, and I don't expect you to be able to just see that without doing some work first, but you do this long enough and you can see it. So what I'm going to do is I'm going to make my denominator 6n squared by first canceling that n with that n, and then I'm going to be left with the limit as n approaches infinity of negative 64 times n plus 1 times 2n plus 1 over 6n squared plus, and here it's going to be 96n times n, that's an n, I don't care what, and let's fix that. That looked awful. Let's fix that. N plus 1 all over 2n squared. And to make this 6n squared, we're going to multiply by 3 over 3 to get our common denominator. Well, 96 times 3 is 288. So I'm going to have the limit as n approaches infinity of, and I'm going to multiply this out. So negative 64 times 2n squared plus 3n plus 1. I just multiplied these two binomials with each other over 6n squared plus 288n times n plus 1 over 6n squared. Now I can simplify yet again. And I'm going to do that by distributing the 64, well, really the negative 64. So the limit as n approaches infinity of negative 64 times 2 is negative 128 n squared minus, distributing the negative, 192n minus 64 plus 288n squared plus 288n all over 6n squared. And right now I can see that I have a second order polynomial in the top because my biggest power, I got a 2 there and I got a 2 there, and my order of my polynomial on the bottom is 2 as well. So I can combine these like terms, and I get the limit as n approaches infinity of 160n squared minus, plus, doesn't matter, plus a bunch of other stuff that I really don't care about, over 6n squared. And now I know that this equals 160 over 6, which equals 26 2/3. And there is the area under the curve between x equals 0 and x equals 4. You have just done calculus. You are Newton. So now I want you to do one on your own and pause the video, do it on your own, and then we will do this together. So this equals the limit. Now this makes it easy because a is 0 here again. So the limit, the limit as n approaches infinity of b minus a over n times the summation as from I equals 1 to n of f of a plus b minus a over n times I. So I know b is 1 and a is 0, so the limit as n approaches infinity of 1 over n, b is 1, a is 0, 1 minus 0 is 1, times the sum from I equals 1 to n of f of, again, a is 0, b minus a is 1 minus 0, or 1, so this is just simplified to I over n. Now we got the limit as n approaches infinity of 1 over n times the sum from I equals 1 to n of I over n squared, right? Because f of x is x squared. That means f of I over n is I over n squared. So now I got the limit as n approaches infinity of 1 over n times the sum from I equals 1 to n of I squared over n squared. N squared is a constant, so I can bring that out front, and that gives me the limit as n approaches infinity of 1 over n cubed times the sum from I equals 1 to n of I squared. And I know what the sum of I squared is. I'm going to carry that on down here. The limit as n approaches infinity of 1 over n cubed times n times n plus 1 times 2n plus 1 over 6. Again, this to that is property 5. Now we continue. We go with canceling this 3 with that, and that becomes a 2. So now I'm going to multiply those two together, and I get the limit as n approaches infinity of, and I'm going to multiply these two polynomials together, 2n squared plus 3n plus 1 over 6n squared. And look, I have a second order polynomial divided by a second order polynomial, which means I just take the quotient of the leading coefficients, which equals 2/6, which then reduces to 1/3. And the area under my curve is 1/3 between 0 and 1. Very good. So we have, for the purpose of this section, we have understood the term of summation. We found the limits of summations. We've used rectangles to find approximations of shaded regions, and we've used limits of summations to find the areas of plane regions underneath curves. Very good job, ladies and gentlemen.